This is the second part of the Drawing Lewis Structures video. We're going to go back in more detail over the rules, the patterns of drawing Lewis structures, and to draw some more drawings, as well as to talk about the results when we're finished drawing those Lewis structures. There's some analysis that we can do. So just to remind you, a Lewis structure is a two-dimensional picture of a molecule, and we're going to work in another lesson on what the three-dimensional looks like. But what you're going to do when you draw a Lewis structure is you've got to start with what we call a skeleton, which is just the general arrangement of the atoms. Who's in the middle? Where are the things surrounding it? Okay, so the molecules that we're dealing with, the simpler ones right here, they're going to have a central atom and they're going to have surrounding atoms bonded to it. Okay, so to determine the skeleton, to pick the middle atom, if carbon is present, it's usually a central atom. If carbon is present more than once, usually the carbon atoms are joined together in a chain to start that skeleton. That's what you see a lot in biology, is carbon chains. Okay? Hydrogen is never, ever, ever a central atom. It only ever forms one bond, and if you only have one connection, you can't be in the middle of anything. To be in the middle, you have to be able to form at least two. So hydrogen is never a central atom. The halogens, which are group 7A, so fluorine and chlorine and bromine, iodine, and actinium, they usually only form one covalent bond. Usually they're not in the middle. That doesn't mean they can't be. So it is possible for them to form more than one bond. So be aware of that. But if you had to choose between oxygen or phosphorus or one of the halogens, halogen's generally not in the middle. Okay. Oxygen forms usually two covalent bonds, okay, and sometimes it's a central atom, sometimes it's not. Sometimes it links two carbon atoms in a carbon chain, so it can do various things. The rule that you're mostly going to follow, because we're drawing simpler molecules. In simpler molecules, the atom that appears only one time in the formula will usually be in the center. Okay, so you got to determine the skeleton. So when you're doing that, once you determine the skeleton, you're going to arrange the available valence electrons around each of those atoms. So you've got to know, and that's what I'm going to harp on, is you've got to know how many valence electrons you have. So you've got to add those all together and know how many you're going to possibly draw. Okay? We're going to see one today where if you're dealing with a polyatomic ion, you have to take into account the electrons that were used to form the ion. So if it's a negative ion, you've got to add on electrons. If it's a positive ion, you've got to remove some. Okay, but when you're drawing this, you're going to put a pair of electrons between each two atoms in the skeleton. Those represent covalent bonds, and those are called the bonding pairs. Then, after you've connected all the middle ones to the outer, or the middle atom to the outer atoms, you're going to use the remaining electrons to complete the octets, which is, remember, 8 of all the outer atoms. Those are called non-bonding pairs or lone pairs. And then any electrons that are left over after you've done that, those are added in pairs to the central atom. Okay, so those are general rules. We're going to see a couple exceptions that we'll look at. And so I'm going to come back to this. But what you're generally looking for is the central atom should have an octet. You're looking to try to draw a drawing where that central atom achieves 8. But there are a few exceptions that are common that we need to be able to look for. So the central atom may have fewer than 8 if it's boron or beryllium. We have found in nature that those two atoms will form bonds and molecules, and they will not achieve an octet. And they just are, so we have to draw molecules that represent that. Okay, if it's not one of those two and it's lower than 8, you're going to have to form what are called double bonds, which we're looking for in order to obtain an octet. So we will definitely look at that. And then there is a rule that the central atom may have more than 8 electrons if it falls in periods 3 through 7 on the periodic table. So where the 8 electrons comes from is the S and the P sublevels. And a full S and a full P added together is 8 electrons. So that's where our octet comes from. However, there are more sublevels that we've looked at. The next one up would be the d orbitals, okay, which can hold an additional 10 electrons. So if an atom has d orbitals, it can hold up to 18 valence electrons. So why this little note says if it falls in period 3 through 7 on the periodic table, starting in energy level number 3, that is the first time we have d orbitals. So there's a 3d and a 4d and a 5d, 6d, and 7d, but there's no such thing as a 2d or a 1d. So those are not allowable. So if the element falls on periods 3 through 7, it may have more than 8. It does not have to. We just have to go with what we see in nature, what molecule we're actually drawing. All right, so we're going to pick up drawing. We drew 4 structures the other day on the first video, so we're going to draw 6 more. Okay, so first up is methyl chloride. So to be able to draw this structure, you do have to know the chemical formula. A lot of the times these simpler molecules will follow those nice little covalent naming conventions that we learned in the fall with the prefixes. Organic compounds, things with carbon, have their own structures and names, so some of them I'm going to have to help you out on. But methyl chloride is CH3Cl. So the thing that I'm going to harp on you most is count the number of valence electrons first. Get that done first so you know how many electrons. So just to remind you, what we do to count the valence electrons is go look at the periodic table and we go look at each element. So we've got carbon, and to check its valence electrons, we look at its A group number. Okay, we could write the electron configuration or we can do it quickly. Say carbon has 4. We find hydrogen, and we see that hydrogen has 1. But we have 3 hydrogens. So we're going to have to multiply that by 3. And then we go find chlorine, and chlorine has 7. So we add on 7. Okay, so if you come back here and we add these up, we get that there are 14 electrons. That's what I got to draw. So then I'm going to decide on a skeleton. And so per the little set of rules that we looked at, carbon's going to go in the middle. And then I'm going to have 3 H's, doesn't matter where, and a Cl. Then I'm going to connect each atom on the outside to the middle atom with 2 electrons. All right, so that at that point I've drawn 8 electrons. Remember, electrons are shown by dots. We have another convention that we can use. We can use a single line to represent 2 dots. It is completely up to you. Okay, but that's still just 8 electrons, and we need to draw 14. Okay, so then we're going to go to the outer atoms, the ones around the middle atom, and we're going to try to complete their energy levels. Well, hydrogen is at energy level number 1. It only has 1 energy level, and hydrogen is complete after just 2 electrons. 1s2 fills it all up. Okay, so hydrogen actually will never have any lone pairs around it. Hydrogen's good. Okay, each one of these hydrogens has 2 electrons around it. So the one that's missing its octet, though, is chlorine. Chlorine is energy level number 3. It can hold up to 8, or it can hold more than 8, actually. But we want to complete its octet. So we're going to go 2, 3, 4, 5, 6. So that now our chlorine has 8 electrons in it. And now if I count my total number of electrons that I've drawn 14 electrons. All of my outer atoms are good, circled in green. They all are full energy levels. I do have to go back and I have to check my central atom. So all of the bonding pairs, the ones that are between the 2 atoms, are able to be counted for both atoms. Those are the shared ones, and they get counted for both things that are connected by them. So if I look at what's inside the little purple bubble that I've circled, I've got 8 electrons in there. Okay, so then carbon achieves this octet. So this ends up being my Lewis structure. I've drawn something where everybody has a full energy level. And again, you can use a line to represent those 2 dots around chlorine. So that's my Lewis structure for methyl chloride. Okay. So moving on to carbon disulfide. Okay, first I need the formula. So carbon disulfide Okay, then I got to go find the number of electrons, valence electrons. So I'm going to go to my periodic table. I'm going to look up carbon, and we're going to have 4. And I'm going to look up sulfur right here, and I'm going to see that it has 6, but there are 2 of them, so I'm going to multiply that by 2. So when I add this all together, I get 16. So now I'm going to come in here and I'm going to draw my skeleton. So I'm going to put carbon in the middle, sulfur on the outside. And I'm going to go ahead and connect them. I'm going to use lines this time. So I'm going to do 2, 4. So I connect them to the central atom. I still have 12 more electrons. So I'm going to go to the outer atoms and complete their octets. Okay, so the outer atoms of sulfurs and complete their octets. So I've drawn 4 electrons, so I'm going to keep track. 6, 8, 10, 12, 14, 16. So now I've drawn all my electrons, at my 16. I've filled up the octets of the 2 outer atoms. Those sulfurs have their 8. I go back and I have to check my carbon atom. So if I check my carbon atom now, I only have 4 electrons in there. And I needed to achieve an octet. So the only 2 elements that we found that will have lower than 8 are beryllium and boron, as long as they're capable of getting 8. Hydrogen will never have that. Hydrogen always maxes out at 2. But carbon's not good. So this is the first time that we've seen this opportunity to move some electrons around. So we can't draw any more electrons. We can't draw any additional electrons because we've hit our 16. But what we can do is choose to share more between 2 atoms than are currently shared. So suppose that instead of that sulfur having that electron pair as a lone pair, I can move it so it's still within sulfur's valence shell here. So sulfur still has my 8, or the 8, but now I'm sharing it. I'm moving it into carbon's valence shell as well, and I'm sharing it with carbon. So if you look at what's happened now, that sulfur still has 8 within its sphere of influence there, but carbon now has 6. And that's good. We're trying to achieve 8. So I'm going to try the same thing on the other sulfur and draw that in. And so I haven't drawn any more electrons. I still have 16 electrons drawn. But now the way that I've shared them, each sulfur still has 8, but now carbon also has 8. And so this is the Lewis structure that we're going to go with, okay, that is shown for this molecule. These things right here are called double bonds. Okay, it's just sharing more than one electron pair. Alright, so the one thing on that is that every time I teach a double bond, everyone wants to put those in to start with. You should not put in double bonds or triple bonds when we get there. You should not put any of those bonds in there until after you have used all of the electrons, the valence electrons. You've placed them all, and some element is still not full, not reaching the octet. You should have to erase and move a pair of electrons before you ever double bond, okay, if you're doing it right. The reason I can do it now is that I've done it so many years that I know which ones double bond and which ones don't. When you're starting out, if you don't erase to draw a double bond, you're probably doing it wrong, okay? So next up is silicone tetrafluoride. So formula for silicone tetrafluoride, we've got Si and F4. We've got to go count valence, so I'm going to let you count them on the periodic table yourself, but you'll find that silicone has 4 and fluorine has 7. But there are 4 of them. So when I add them together, I have 32 electrons. Alright, I'm going to pick a central atom, so I'm going to pick silicone. It appears fewest times in that structure. I'm going to surround it with the fluorines. Okay, so I have 32 electrons. So here we go. I'm going to 2, 4, 6, 8 to connect to the central atom. Then I'm going to go fill up my valence. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's all my electrons. So as I did this, I filled up all of the valence for the fluorines. Those are all good. They have an octet. So I do have to go back and I have to check my silicone. So everything that's connected to the silicone. and I look and I have 8 electrons in there. So I'm good. I don't have the need to double bond or anything like that. That's my Lewis structure. Okay, and then we've got three different ones to show you some anomalies. So first up is nitrate. So nitrate is NO3, and all year long I've been harping at you how important it is to show that charge. Okay, so NO3 negative. And I'm going to draw the 1 negative in here for a reason on this one. But you have to have that when you draw nitrate, otherwise you're not going to get the right structure. So if you look at the periodic table and you find nitrogen, you're going to find that it has 5 valence electrons. Oxygen has 6, but there are 3 of them. So then what does this -1 mean? And so what the -1 meant, remember that protons we never ever change for regular chemistry, that's nuclear. And so a negative or a positive charge means we've messed with the electrons. So to become a negative charge, you have to end up having more negatives than positive. So what this -1 meant is that this structure as a whole has added on 1 additional electron. It has stolen it from some other atom. So when we count our valence electrons, you're going to have to add that 1 additional electron when you're counting to be able to make sure you have the right valence electrons. So when we add this up, we get 24. That's the really important different part about this structure. Now we're going to have to go do all the rest of the same steps that we've done for the other one. So nitrogen's going to go in the middle. We're going to have 3 oxygens around it. Okay, so I have 24 electrons. So I'm 2, 4, 6, connect them all. Then I'm going to go around the outsides, 8, 10, 12, 14, 16, 18, 20, 22, 24. So then I go back and check, and I have filled up all my valence for my oxygen. So I go check my nitrogen, and I see that my nitrogen only has 6 electrons. And it's not beryllium or boron or hydrogen, so I need an octet. And so this is where I've drawn all 24 electrons. I have to go move a set of electrons, so I'm going to have to do some erasing. Okay, so on this one in particular, this is the structure that I did want to talk about. I could choose to move the electrons from this oxygen. Okay, and I've achieved my 8. And I'm done. I don't have to do it again. Okay, I don't have to double bond anymore. That's a valid structure. Okay, but I'm going to draw another one over here. I'm going to duplicate the structure very quickly. I could, instead of choosing the oxygen that I drew at the bottom, what if I chose the one on the left side to double bond? Okay, and I checked again. Okay, my oxygens are all still good, and my nitrogen has 8. Similarly, I'm going to draw one more, and there's a reason why I'm drawing all of these. Okay, if I chose the oxygen on the right to double bond, my oxygens still have an octet in their valence, and my nitrogen also has an octet. So all 3 of these structures are identical and all correct. And so this has a name, this ability to draw more than one correct Lewis structure with our rules. And remember, a Lewis structure is just a 2-dimensional drawing of the molecule. But these are all equivalent to each other. There's no difference. And these are called resonance structures. Okay, so a molecule is said to exhibit resonance when more than one correct Lewis structure can be drawn by simply choosing a different atom to double bond. Okay, but that they're all identical. Okay, it doesn't really matter. I could have rotated this original drawing and so that it looked like one of the other 2. So these are called resonance structures. And they're all identical, and these are our 2-dimensional approximations. You don't have to draw all 3 unless you're instructed to draw all the possible resonance structures. Okay? But what you have to understand is that the molecule itself, it's not that one of these gets chosen to double bond and the others don't. Okay? The molecule exists as what is called a hybrid, a resonance hybrid. And if you know anything about hybrids, where we deal with cars or animals or anything like that, a hybrid is a mixture of the different possibilities that were put into it, and to come out with one resultant thing. And so the hybrid actually exists where this double bond is essentially split between the three options and delocalized around those. You don't have to worry about too much about that right now at all. You just have to know that there is more than one possible, and so someone else could draw a different one that would be completely right. Okay? You would only have to draw one possible right now. Okay? So we're going to leave it as that original structure that I drew. Okay? And this is just one possible resonance structure. The other thing that's kind of convention on this, okay, when you draw a polyatomic ion that has a charge, convention says we typically put the structure in a set of brackets and we show the charge on the outside so that someone coming along that did not have the advantage of seeing what we just drew, they just saw the structure, they would know that where that extra set of electron or that extra electron came from, that it was NO3, because they can see in the structure that we have one N and three O's, but they don't know where the extra electron came from. So convention says we're going to draw it in brackets and include that -1 so that they know we drew nitrate. Okay? If you leave that off, it's not that big of a deal, but I wanted you to recognize that that's conventionally what we do. So we're going to try another polyatomic ion, carbonate. Carbonate is CO3 with a 2-. So when we go add up the electrons, we're going to have 4 for carbon, 6 for oxygen, but there are 3. And then this -2 means we add on an additional 2. So if you add this up, you get 24 electrons. So we're going to pick a skeleton. So I'll put carbon in the middle and 3 oxygens. I'm going to connect them all, 2, 4, 6. Go around the O's, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, I'm going to check my valence. My oxygens are all good. My carbon is not. It's short 2 electrons. So it's the same thing that I did for nitrate. I'm going to have to double bond. Again, with this structure, I can kind of choose. So this is another one that's said to exhibit resonance. Okay, and I just get to choose. So this time I'm going to choose the one on the left. Doesn't matter. Okay, this is one of the possible structures. All right, and then to finish it up, I'm going to put it in brackets with a 2-. So that's one of the possible resonance structures. All right, and last one that we're going to draw before we go back and talk about some things. All right, boron trifluoride is BF3. Boron, when you look it up, has 3 valence electrons. Fluorine has 7, but there are 3 of them. So I'm going to get 24 electrons again. I'm going to put boron in the middle, fluorine around it. We'll connect 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've reached my 24 electrons. I check my valence. All my fluorines are good. I check my boron, and it's not. However, boron was one of the 2 elements that we have found, along with beryllium, that will form molecules and not achieve an octet. This is the actual structure for boron trifluoride. There's no reason to double bond. This is it. There's no reason to put it brackets with a charge. It's not a polyatomic ion. So we're good with boron trifluoride. Okay. So there's lots of structures that you can draw. These are just some that we practiced. You can definitely go practice more. So we're going to talk about some details of these structures to end this. So this is not a big deal, and it's nothing that you'd have to draw or identify. But there's something called a coordinate covalent bond, where one atom in the structure provides both of the electrons in the bond, so that some other atom provides nothing. And this is not one that we've drawn so far, but you have seen ammonia this year, and the hydrogen ion. So if you drew the electron, the Lewis structure for ammonia, this is what it would look like. And hydrogen ion, which is what we use for acids, hydrogen ion doesn't actually have an electron at all. But we have learned that there is a polyatomic ion called ammonium, which is NH4+. And so what ammonium is when you add this extra H+ onto this ammonia, and where it gets added on, why this happens, is that you actually have this lone pair of electrons sitting on the nitrogen, that can form that bond. So ammonium actually looks like this, okay? But these electrons right here that were connecting that last one were donated completely by that nitrogen. That's called a coordinate covalent bond. Not a big deal, just a note for you. Okay. Next thing we're going to look at is formal charge. So we're going to go back through our drawings and calculate some formal charges on a couple atoms. Okay. So what a formal charge, you're going to give a formal charge to every element in a structure. You can give each one a charge. So remember, these are covalent molecules, and so they don't have individual charges. Okay, but these formal charges, what they are, is the difference, so there's going to be a subtraction, between the electrons that an atom has in the Lewis structure and the number of its valence electrons. Okay, and so there's a formula for this. How you calculate formal charge is you take the valence electrons and you subtract, and then there's a set of brackets here, so you have to do an addition first. You subtract the total of the number of non-bonding electrons and half of the number of bonding electrons. So there is a formula there. I'm going to do a little bit simpler. So how I calculate formal charge is you do take the number of valence electrons, so the number of electrons that the element brought to the structure. That was when we went and counted up the total number of electrons. That's where we got the valence electrons. Okay, and then we're going to subtract the electrons that are physically butted up against that element in the structure. Okay, and this is way simplified, but what that ends up being is the number of non-bonding electrons plus half the number of bonding. So I'm going to show you that with 3 molecules up here that we've already drawn. Okay, so I'm going to show you these 3 molecules, how to calculate the formal charges. So each element in the structure has a formal charge. So you have to do a calculation for each individual element. Okay, and so the first couple, they're not going to seem that interesting. They may not at all seem interesting, but what you're going to do is you're going to pick each element. So we're going to look at methyl chloride first. Okay, so we have to pick an element to focus on. So let's say we focused on carbon. Okay, how you calculate its formal charge is you take how many valence electrons it has. So how many electrons it brought to the structure. So we have 4. And then we subtract how many electrons are physically butted up against it. And so what I mean by that, so that you avoid that formula, is in the structure, if these were dots instead of those lines, which I started with, how many are physically butted up against there? Which is also 4 here. So that formal charge is 0. Okay, so let's say I want to look at the chlorine. And so I look down here at chlorine, and I say, how many valence electrons did this chlorine bring? That was our 7. Okay, so I take 7 and I subtract. Okay, and then I'm going to look at how many electrons are physically butted up against that chlorine. And so I have 1 here, and then I have both of these, and both of these. So that is also 7, which comes out as 0. So the formula that I showed you on that slide said to take the number of non-bonding electrons, which are all of those, and then half the number of bonding electrons, which is why I only picked 1 of those. So that's why I'm doing the ones that are physically butted up against them, because that's where the half comes in. Okay, and you can use the formula, or you can use this little technique. It doesn't matter. You'll get the same answer if you do them right. All right, and then if we focus on the hydrogens, so let's say if I focus on the hydrogen on the left, okay, this hydrogen brought 1. Remember, each one brought 1. And then how many electrons are butted up against it? I just have 1. So I get a formal charge of 0. each of these other hydrogens looks the exact same, you're going to get a formal charge of 0 on all of them. And so looking at this molecule, you're like, well, everybody's a 0. Yes, in a lot of our simpler structures, everybody does end up as 0. Those they've actually found, those are usually the best structures to draw, or the ones that nature chooses to bond, ends up where the formal charge of everybody, if possible, is 0. Okay? And if they're not 0, then it has to deal with, if they're not possible to be 0, then the rules of electronegativity, which was last unit, kick in. And so there's a little more complicated stuff to that, but I just want to teach you how to calculate it today. Okay? And so we're also going to look at F and H. So F only has 3 elements to choose from, or to do formal charge on. So we're going to start with carbon. So carbon brought 4 to the structure. So we're going to say 4 minus. And then we're going to imagine if every one of these lines had dots instead. So remember the dots, the lines represent 2 dots each. And so if we look at carbon and we say, okay, how many dots are butted up against carbon? There are 4. So we get a formal charge of 0. And then if we repeat the process with sulfurs, okay, sulfur brought each sulfur, let's say I'm doing the one on the left, sulfur brought 6 to the structure, and then we subtract how many are butted up against it. And so we have 1, 2, 3, 4, 5, 6. So we get a formal charge of 0. The sulfur on the right looks exactly the same. We have a formal charge of 0. Okay? Alright, so the other thing with formal charges is that whatever your formal charges are, they have to add up to the charge of the overall structure. So all these zeros nicely add up to the charge of CS2, which is nothing. Okay, so the reason that I picked H to do as an example is that H has a charge that is not 0, and so these can't all be zeros when we add up the formal charges. Alright, so let's focus on the nitrogen. Okay, nitrogen brought 5 electrons to the valence total, and then we're going to subtract how many are physically touching it. So if I drew these in as little dots, we have 1, 2, 3, 4. So nitrogen has a formal charge here of a positive 1. Alright, so then let's focus on one of the oxygens. So the oxygens here, remember this was a resonance structure. The oxygens in my structure look a little different from each other. So let's say I look at the oxygen down on the bottom. So this oxygen, each of the oxygens brought 6, but I'm going to subtract how many electrons are physically butted up against it. So for this oxygen I have 1, 2, 3, 4, 5, 6. Alright, so that gives me a formal charge of 0. Alright, so then let's say the oxygen on the left. That oxygen brought 6. When I go count how many are physically butted up against it, I have 1, 2, 3, 4, 5, 6, 7. That formal charge is a negative 1. If I go do the oxygen on the right, I have 6 minus, because all the oxygens brought 6. I do it again, 1, 2, 3, 4, 5, 6, 7. So I get a negative 1. Now if I look at all my formal charges, okay, I only have 1 0 this time, but I have a negative 1, a positive 1, a negative 1, and a 0, and those all add up to be negative 1, which is the charge of my overall formula. Okay, so those are formal charges. That's how you do it. Okay, there's a lot deeper level on trying to choose correct structures and all that kind of stuff based on it. All you'd have to be able to do is calculate it right now. Okay, all right. So the last concept we're going to discuss here is bond energy and bond length. Okay, these are related to the drawings that we just did, but we want to look at how strong a covalent bond is. How strong is that connection between those two atoms? Okay, and so it depends on how big that attraction is. But there's a couple terms that we're going to learn. So bond energy, which is a big deal when we get into AP Chem or Chem 2, is also called bond strength, how strong that is. It's how much energy you would have to put in to break that bond, to overcome that attraction. So if we drew something where carbon is bonded to some hydrogens, bond energy is talking about how much energy you're going to have to put in to rip this hydrogen away from this carbon, or the carbon away from the hydrogen, to sever that bond, okay, so that these guys would move away from each other. And those electrons that were shared now would either have to be split or more likely go with just one of the atoms, okay, and leave one without any of them. So, but bond energy is how much energy you would have to put in to actually physically separate those two, okay. And then bond length. Bond length is physically, or is exactly what it sounds like. It's the distance between the nuclei of the two bonded atoms. So how far, so if you have the nucleus and the nucleus, how long is that bond? How far apart are those two things? So there's a big relationship between bond length and bond energy. Okay, there's also a relationship between what's called bond order. And so what that is whether there's single bonds, which is one connection, double bonds, which is two connections, or triple bonds, which we haven't drawn at all in the examples, which are three connections. Okay, that's what bond order is. So there's a relationship between the two of them. And so the idea is as simple on bond length and bond energy. If I had two people holding some kind of thing, they're both holding onto some kind of rope, and I'm asking someone else to come in, run through that rope, and break those two things apart. Either rip the rope or paper right in half, or rip it so that one person ends up with all of it. The further apart these two people are from each other, I just decapitated that person. Okay, the further apart these two are from each other, the longer that bond is, the easier it is to be able to break that apart, to run through that. Okay, the closer they get to each other, okay, and the shorter that bond is, it's going to be much harder to break. Okay, so shorter bonds are stronger bonds. Okay, just period. Shorter bonds are stronger. They're closer together. Okay, the other thing that can affect the strength of it is whether they're double bonds or triple bonds. So imagine they were holding two of those ropes. It's going to be harder to rip through or to break that connection when there's two of those, and even harder if there's a triple bond, three of those connections. So the higher bond order, which means there's more bonds there, double bond, triple bond, will give you a shorter bond length and a higher bond energy. It is harder to separate those. Okay, and so we're gonna try with some examples to arrange them. But this is just a table of some bond energies. In no way would you ever have to memorize them. But some things that I wanted you to note. Okay. These four in particular, right here. The H to F, the H to Cl, H to Br, and H to I. If you look at the bond energies, it looks like it's H to F is the strongest bond. And so why that's true, okay, you have to take into account what we learned last unit about atomic radius. And so these four elements I picked because they're the halogens. They're all in a family. The atomic radius gets bigger and bigger and bigger between these elements because of the additional energy levels of electrons that each one has. And so the bigger and bigger those atoms get, the longer and longer that connection has to be, because you can't get that hydrogen in closer. And so the longer that connection is, the weaker it is. So I did want to make a connection for you. We learned earlier this year that HCl, HBr, and HI were all considered strong acids. And what that meant was that the H popped off completely. Okay, they separated. And we learned that HF is a weak acid. And what that meant, it didn't mean it was not scary or dangerous or anything like that. It meant that the H didn't come off very much. Okay, and why the H didn't pop off much is because it is much harder to rip that H off of HF because that's a stronger bond. Okay, because it's shorter. So the other thing that I wanted you to look at is comparison of the same kind of bond, but doubles and triples. So if you look at the carbon to carbons, we have one with a single bond that would cost 348, and these are all usually in kilojoules per mole. And the C to C double bond is 614, so nearly double that. And the C to C triple bond is 839, so even harder to break. So the ones with the higher bond order, the more bonds, have a much higher bond energy. Okay. The other thing is the bond length that I wanted you to compare. And so if you look at those same three that we just looked at, the carbon single bond, double bond, and triple bond, these are bond lengths, so how far apart they are from each other. The more bonds that you have, even if you're the same element, the shorter that bond is. Okay, just it's more connections that pull those molecules in or these atoms in tighter. Okay, so we're going to see if we can rank them using the periodic table. All right, so the directions here say we're going to rank, we're going to do two different rankings. So we're going to start on one. We're going to rank them in order of decreasing bond length. So bond length, that's what we're dealing with first. We're going to ignore the strength right now. But decreasing for that would mean long to short. That's what we're going to do first. Okay, so decreasing length would be the longest to the shortest. So we're going to examine A. We've got S to F, S to Br, and S to Cl. So the things that we want to look at first, they're all the same bond order. We have single bonds with all of those. So then what we have to look at for the length then, if they're all the same bond order, is we're going to look at the sizes of these elements. So sulfur is the same each time, but we've got fluorine, chlorine, and bromine. And so the longest connection is going to be with the biggest atoms. They're just going to be naturally farther away. Okay, so the longest bond is going to be between the S to Br. Okay, then we've got S to Cl. And then the shortest is going to be the S to the F, because the F is the smallest. All right, so we're going to do the same thing for the next set on B. These are all the same elements, so the same sizes, but they're different bond orders. We've got a double bond, a single bond, and a triple bond. The longest is the single bond. Then we've got the double bond. And then the shortest is going to be the triple bond. Those most connections. All right, and then the last one, we've got same bond order, so they're all single bonds, but now we've got different elements. So here we're looking at silicone with carbon, with oxygen, and with fluorine. So this one's a little trickier. You got to go back and remember atomic radius. These all have 2 energy levels, but if you remember what happens to atomic radius is it decreases across the periodic table because even though they have the same energy levels, they have more and more protons which pull in the electrons tightest. So the biggest atom here out of carbon, oxygen, and fluorine is carbon. So that's going to be the longest bond. Then we have the oxygen, and then we have the fluorine. Fluorine is the shortest because it has the most protons in that same energy level. Okay, so that is how to rank them on bond length. So now we're going to come in, and we've got another set of directions to do. Okay, it says we're going to see if we can rank them in order of decreasing bond strength. So same sets. So decreasing bond strength means strong to weak. So I got rid of the periodic table because we already have looked at all the stuff that we need for here. Remember that a stronger bond is a shorter bond. And so when we look at A, if I want to know the strongest, it's going to be S to F, then S to Cl, then S to Br. So the longest bond should be the weakest bond. The strongest bond should be the shortest bond. All right, so what you'll find is these are inversely related. They're opposite related. So the next one, the strongest bond is going to be the triple bond, then the double bond, and then the weakest is the single bond. And then finally, the strongest bond here should be the shortest bond with F, and then to O, and then to C. Okay, so those are oppositely related. Strong is short. Okay, strongest is shortest. All right, and that's it.